doing a spray bond around here? Yes, there is. And is there any paper towel?
I got that.
Can you bring it up? I mean, I've seen this thing in bad shape. It's about as worse, as bad as it gets right now. Go ahead, take that in. I don't know if it's going to help. Somewhat. Anyway, I want to tell you one thing about the Fourier transform right now. If you understand the Laplace transform, the Fourier is trivial, just in my opinion. There's one trivial, and there's one thing about it, though, that is different. And that is the fact that the series now technically can begin at minus infinity and go to plus infinity at the time that, boy, that's lousy. Who is in here? All right. I'm just going to, I think that's why it's going to get told about. All right, thank you. Thank you very much. All right, so let me go through this. First, any other questions about what we talked about last time? Yes?
I'm looking at the sawtooth.
The what?
The sawtooth problem
Yeah.
for the homework. And I still don't get how to get C in. I get how to get C out and
C0.
Yeah.
You're talking about, is this the one for homework? I mean, the problem I gave you to do on for Friday.
No. This is homework 13.
All right, what does the waveform look like? If this is x of t, you gotta help. Where do we start at t equals 0? I know. What is
At
it?
5.
What?
5. And it goes to 2.
What?
2. It goes
It goes down to 2.
Oh, like this?
the other way. Sorry.
Wait a second. Hold it, what do you mean the other
No,
way?
sir.
It starts at 0, 0.
Oh.
To 5.
It starts at 0
Yep.
and it goes to 5,
Yep.
right? And it repeats itself?
Yes.
And it does it just.
This is the straightforward one, I think. Right? Look, we'll do it. Guys, I can't spend a lot of time on this, but I'll go through this. If this is x of t, first you have to realize it's periodic. Do we all agree there? It's periodic. If it is periodic, it definitely can be defined in terms of a series. C of n e to the j n omega naught t, right?
But the
N equals minus infinity to infinity. Do you agree with me?
on there they wanted it in cosine.
That's all right. Remember how I showed you take that series to cosine? You remember that? How many do? Nice. You got to be attentive in the lecture. Look, I'll break it out for you over here. I said that if you had a periodic waveform, it could be broken out, right, as a summation from n equals minus infinity to infinity of C of n, which is a magnitude in phase, e to the j n omega naught t. Now that C of n is the thing you're worried about with that sawtooth. That's the only thing you're after, right? By the same token, it can also be represented as C0 plus the summation from n equals 1 to infinity, right, of 2 times the magnitude of C of n times the cosine of n omega naught t plus the phase angle of C of n, right? Isn't that right, class? How many remember this right here? That C of n is the same C of n there. Now this is the coefficient. It's a strip real. How many recall that? Right? So I think what you're asking is how to get this value and the phase angle. It's the same as this value, the C of n of the original one. How do you do it? Just tell me. Do you know? Or how many know? You're gonna be quizzed, you're gonna definitely be asked about this. This is as straightforward as it gets. What do we do with this thing, class? A derivative with respect to time, right? After doing the derivative, what do we get? This is t, right? 2, give me a second. Now first, I'm gonna break this out here. What is C0 just by inspection? Take a look at this. 5 over 2 or 2.5, right? 5 halves. This is something that doesn't take any energy at all, just by inspection. Now we've got C0. Now, when we take the first derivative, what do we get? We get a spike, right? From, it goes, wrong direction. Just follow. Y'all agree it goes from 5 to 0, so we get minus 5, a delta function, correct? Right? Y'all give me that? If it goes from 5 to 0, that's a delta. Then it stays what? A slope of 5 halves. So then you have this, and this is x prime, by the way. And it just stays there. Then here, boom, another delta function stays there, right? Boom. You all agree? Bunch of delta functions at the period, at 2, 4, 6, 8, right? Plus a constant. Agree? You asked about this. Do you all see that? You see this right here? Now, when you do this, you break it into 2 functions. You break it into the first function, just delta functions, it's periodic, plus the second function, that's just the DC value. Correct, class? Your question is usually, well, what about the point where the delta function occurs? Don't worry about that point. It looks as though it is a straight DC waveform with delta function superimposed on it. Follow me? So don't concern yourself or think too deeply about this point. That is still DC, basically. All right? Even though technically that delta function occurs at, a time that can be subdivided kind of deal. It's so small, it occurs, but at that time subdivided, theoretically you could say, well, this DC function goes to 0 again, but it really not. I'm just telling you that. You can assume it's just flat. So I can say this waveform in itself can be broken down into 2 waveforms. I'll call it x1 prime of t, that is just going to be delta functions at 0, at 2, at 4, and so forth, plus a second function, which will be at 2, 4, 6, 8, an x2 prime of t, that'll just be the DC value, which is the slope of that line, which is 5 halves. And I know there's some ill will about what happens at these points. You don't worry about it, it's DC. Understand, class? Yes, sir.
So the delta functions will go to 5, like negative 5 halves?
Yes, I didn't put it down here, but it goes from 5 to 0. This is minus 5 here, minus 5, minus 5. Not 5 halves, but minus 5. Right? It goes from 0 down. Look at this. I'm up at 5, right?
Right.
I go to 0. That's a weight of 5 with a negative sense. Minus 5. Minus 5 here, here, and here. They're all delta, right?
So when
But
you
then there's a constant slope of 5 halves also.
right.
That's it.
Okay, so when you add them together,
Then you get this. If you add that plus that, you get this.
okay.
You follow me on this? So I'm breaking it apart into 2 series. Now, question for you. What's the derivative of this with respect to time? Forget about it. The real truth of the matter is, without getting into a lot of the development, this is associated with the DC value that we've already got, the C0, so we forget about it. The only thing we need is this value. We need to see this C event. Understand C event prime from this. And I'm going to get it. I think you can get it with me. These are great questions because it's the obvious thought in everybody's head. Well, if it's a delta function at that point, it can't have a DC value there. That's the common thing you think about. But I'm telling you, you forget about that. It's DC at that point. Understand? There is no change. It doesn't go down to 0 at that point. Just assume it's DC all the way across. Are you with me on this, class? You may not like it, but trust me, this is the way it works. So then I get down to this point. Now I need x1 prime. I need Cn1 prime, right? I know that's 1 over the period, the integral. Here, I'm going to go from, since I want to integrate over a period, I'm going to start here, stop here. That's going to be my period. Understand? It's 2 seconds long, but I've shifted the beginning, so I don't start at the delta function. Does that make sense to everybody? And I know what Cn prime will be. We'll start at some point less than that, call it minus epsilon. It goes to minus epsilon plus the period t. We know t is 2, just leave it as t for now. Yes?
In the x1 prime of t, wouldn't the amplitude be negative 5 instead of negative 5 halves?
Gonna have, oh, yes, I'm so sorry. I'm in a hurry and I should stop being in a hurry. It's minus 5. You're absolutely right, that was my bad. I guess I'm thinking ahead of what I need to do, but we'll cover this, we'll get this problem done once and for all. This is a trivial problem, by the way, it's not very hard. It is one of those problems, though, you ask yourself, what about that point? Does this thing, this DC part right here, should it have, I erased it, should it have a hole right there at 0, 2, and 4? No, just leave it a constant. Following? Now, what's this going to be? Well, here I have minus 5 delta of t, that's the only one that happens, e to the minus jn omega naught t dt. What's that going to be? We know the period is what, class? 2. It's 2, so now I have 1/2 times 5, or minus 5, right? And what happens, what is this integral? Delta t to the minus jn omega naught t dt. Class? When does the delta function turn on? T equals 0. What is e to the 0?
1.
1. Therefore, it's 1, right? It's simply 1, isn't it, class? So it's simply minus 5 halves. It's that easy. That's Cn1 prime. What is the actual C of n then? For all values of n unequal to 0? Class? C of n would be what? C of n prime divided by jn omega naught. So it would be that minus 5 halves divided by jn omega naught is 2 pi over the period, which is 2 or pi, right? And that's C of n for all values except n equals 0. Do you follow me? What?
I don't know how you got negative 5 now. Like, how you got the 1 and negative 5.
You see this is minus 5 for the delta. So when we get C of n, don't we all, or C of n prime, we take 1 over the period, right? That's 1/2, right? Then we put x prime here, of t, right? X prime of t is minus 5 delta t. When we do this integral, don't we get minus 5 times 1 divided by 2? That's it. Agree, class? How many see this? Yes?
And the reason you didn't integrate the other one was because the derivative of that.
I know when I take, I need delta functions, so when I take a derivative of the DC value, it becomes 0, right? If it's constant. The derivative of x with respect to time would be 0. Do you agree, class? That's the reason I don't need to bother with that part. All right? So now, this is my C of n, right? Can't I take that j, 1 over j is what, class? Minus j. I can make this simply 5 halves, right? N pi times j. Isn't j just what? 1 at an angle of 90 degrees? So the phase of that is 90 degrees, and the magnitude is simply 5 over n, or 5 halves divided by n pi. And that's what I have in the program, if you look at my program. You all see this, class? It's extremely trivial. You have to spend time with this or you'll blow these. Do every single problem on your own. But then it will be so easy that these things will just, you'll fly through them. You'll kind of laugh at me that I even gave you. Sort of like that last quiz. If you've done the homework and kept up, that last quiz was a gift. It was a joke. But if you haven't, you were completely confused. And I noticed that it'll always be this way and it gets worse. The further we get in this course, the greater the difference between those that know and those that don't. You'll see people that get zeros and people that get perfects. And it's all based on the work they put in early on a lot of times. So stay up with this. Are we in agreement here? I hope I answered your question. But very easy, and that does agree with what I have in that program. remember, what I'm looking for is the output. So I will leave that in your hands. Now we have the cosine series, right? Okay. And I've done that last time. Do you remember? I developed the output in terms of a cosine series. How many remember that? Good. Okay. Now, to today's lecture. And you mentioned about the test. Now, usually I give a test when I finish Fourier series. If you want to vote on it today, I'm game. It's up to you. You can vote on it Friday or now. You brought it, somebody brought it up. Who brought it up? You? I mean, you've had tests in some of the other classes. We get 2 tests. Remember, you get a quiz every week that takes the place of the test. In my opinion, it also tries to keep you up to date. So you don't just wait until the test and cram and then really control. What, you want to vote on the test? Yes or no? You do? If you do, raise your hand, so I got it handled. Well, that's weak. All right, well, you're going to get a test one way or the other. How about we vote Friday? All right? And I hold you responsible to make sure I don't forget. That means you. All right? And you, Josh, and you, since you keep asking questions. So you 3 make sure I don't forget. Write it down. It's not about us, trust me. So now we're talking about Fourier transforms. I want you to make sure you get this. Yes, sir?
Just a quick question about syntax for like if we do have it on the test and we need to put it in the cosine form for a Fourier series, could we just write angle of C?
I'm going to level with you on an examination or on a quiz. I will ask for the value of C of n only. It would be the exponential form. On the problem that I'm asking you to evaluate, I will want it in a cosine series because that's the only reasonable way you can make a phasor argument. All right, now, because C of n is the only thing you really care about. Don't worry. And besides that, I'm not going to ask you, I will ask you to evaluate C of n at n equals 1 when it's trivial to look. I mean, look at that one I had up there. Evaluate that at n equals 1. 5 over 2 pi. Angle 90 degrees. It's very easy. I wouldn't ask anything more. Okay, are we ready? Now, keep up with this right here. I want to make sure you understand this. We've done Laplace. I'm going to put it up here. Laplace transform says if I have x of t, I can get x of s. And x of s in the old days was the integral from 0 to infinity of x of t, right? X of t times e to the minus st dt. We didn't focus on that, but s itself is defined as some real value called sigma plus some imaginary value called omega, j omega. The j omega term is just like the j omega you had back in the day when you took circuits. There was a frequency, right? That omega is that frequency. The sigma has more to do with stability. And there's going to be a lot more you're going to hear about this in time. The one thing you grab out of all this is when you plotted the poles, right, of a transfer function, if any of the poles were in the right half plane, you knew it was unstable because it would grow exponentially. Do you all remember that? And if the poles were in the left-hand plane, regardless of if they were imaginary components or not, it was stable. And that was the one thing you took from this. We're not going to talk about developing all sorts of systems that will be stable. That comes with Dr. Hung's course a little later. But that's what you took out of it. Now, we're going to do something else. Laplace transforms basically encompass Fourier, and here's why. The Fourier transform is this. It says if I have x of t, now I can get x of omega, and that's equal to simply the integral from minus infinity to infinity of x of t times e to the minus j omega t dt. What it looks like is, it looks like a Laplace transform. It looks like x of s, where s now just becomes j omega, if and only if and only if x of t is equal to 0 for all t less than 0. In other words, if it has no values of consequence, no values that are not 0, for t less than 0. So it means that the function starts at 0. Then you can take the Laplace transform that you know very well and just substitute in j omega for s, and you have the Fourier transform. Can you follow me on that? I'll do you an example to show you what I mean. Just look at these two. What's the difference? Instead of s, I have minus j omega. You'll notice that s is sigma plus j omega, so if sigma is 0, the Laplace is the Fourier if x of t is 0 for all t less than 0, because this integral starts at 0. That integral starts at minus infinity. All right? Now, there's a reason why it does, and it's important. This encompasses a much greater, much larger group of responsive signals. And let me be frank about this. When you do a data record, you record information, then you can have information for negative and positive time. All right? And it means that the analysis doesn't have to be in real time. It can be something where you take a data record and do the analysis on it. Fourier is done for this, and it gives us a lot of information about what's going on in the frequency domain. I'm just going to show you a comparison, or show you something. Now, I'm going to start with the most basic Fourier transforms, and if you have your books, you can look at the tables. I'm going to create some, and you're going to see that the Laplace transforms only with one thing, where you take the value of the actual Laplace transform, and you replace s with j omega, and that's it for a while. So we're going to start by saying, what if I have a signal x of t? I'm going to put x of t here, and I'm going to put x of omega here. We're going to start, here's the definition, x of omega is equal to the integral from minus infinity to infinity of x of t e to the minus j omega t dt. All right? That's the definition. We start, and I start with the most basic of all. If you can't do this one, don't pass, go. Delta t. Now what happens at x? What is the Laplace transform of delta t anyway?
1.
Do you expect the Fourier to be any different? No, but let's make sure it is. Put delta t in here. And delta t is in here. It turns on at t equals
0.
which means e to the 0 is 1. It's 1. Voila. Laplace and Fourier same. Agreed? Next one. What is delta of t minus some, how about I make it that, alpha. So now if there's a time delay of alpha, what happens when I evaluate this? Tell me. Where does that delta function turn on if I put it in there? I don't want to keep writing it in here. At t equal alpha, right? So I evaluate e to the minus j omega alpha, right? And that means this one is 1, this one is e to the minus j omega alpha, right? Do you remember if it was Laplace, it was what? E to the minus s alpha? Do y'all remember that? You see, you just take j omega and stick it where s was. It's that simple for all functions that are 0 for t less than 0. I'm going to show you one where it isn't so. A little later. Now, what about this one? E to the minus at u of t. When I stick it in here, I'll do this one just to show you, but you get it right from the Laplace if you want. This would be the integral from really 0 to infinity, right? Because this is 0 for t less than 0. Of e to the minus at times that, which is really e to the minus a plus j omega t dt. You'll notice how I group the exponentials. I have e to the minus at times e to the minus j omega t. So I group e to the minus quantity a plus j omega times t, and I do the integration, right? You'll notice that looks like a single coefficient, doesn't it? A plus j omega is a constant, is it not? When I do the integral, what do I get? Well, technically I get minus, right, 1 over a plus j omega times e to the minus a plus j omega times t, evaluated from 0 to infinity. I can actually put 0 up here, infinity down here, make that a plus, and it becomes simply 1 over a plus j omega. So this becomes 1 over a plus j omega. I'm going to do something over here and say what x of s is, just so you can see. This is 1, this is e to the minus s alpha. This would be 1 over what? I'm going to put a plus s just based on that, right? You'll notice in every case, if you take s and just make it j omega, you in fact have the Fourier. Follow me, guys? And we can keep going all the way down the line. And you're going to see that they're all the same. You want to do another one? Of all people to say that, you amen that. Well, now that is basically some basic ones that we used what? We actually did the brute force way. We used the fundamental definition to get the transform, right? But what did we know about Laplace transforms as we go down the line? We had a base set, right? We had delta functions, we had u of t, we had e to the minus alpha t, and then we had properties that allowed us to get all the other ones. Isn't that right, class? All the other ones. There's a couple properties that Fourier have that Laplace don't, and I will deal with those in a second. But I want you to hear me. All the properties that Fourier have, Laplace have as well. That Laplace have, Fourier have as well. But the difference is, instead of that s, you have a j omega, and there's some subtle differences in the properties. Instead of like a minus, I say a minus the derivative of x of s with respect to s, all right? It would be a minus j or a j. All right, so I'm going to try to take you through the subtleties. We could populate this, but I'm going to go ahead and take a look at now the properties. What page are the properties on in your book before you transfer? I'm trying to get at the meat of this before. There's sets of properties, right? And let's do a few of them. We'll take the property, and the Laplace property for Fourier. First, if we assume we have x of t here, and we have x of omega here, and we have x of s here. Now we're going to take a look at the properties. All right? And with properties, we know that if I assume I have x of t goes to x of omega, goes to x of s, well, got that redundant here. All right. First property, what happens if I have dx of t dt over here at Laplace? What happens?
You get s of s minus the initial condition.
Right, now this one's interesting. This says x of s, it's actually s, s times x of s, right, minus x, and this would be t equals 0, right? That's a trivial property. Here's one subtlety. Here, we let s go to j omega for the Fourier property, but remember the Fourier transform doesn't start at 0, it starts at minus infinity. Understand? And if you look at the properties, you're going to see this is simply what? This is going to be j omega times x of omega. Look in there. Do you all see that? What's next to that? Is there any other information that you see there?
No, it just says time first derivative. Maybe it shows
It says j omega times x of omega? Nothing else? What did you notice the difference? This part was not included. There's not the t equals 0 evaluation necessary. The reason is that the integration starts at minus infinity. Follow me on this, class? That's the reason. It's an important difference. But fundamentally, it's the same if we have no initial conditions and t equals 0, right? Let's keep going on this. The next one, there's a lot I could do. Dx dt is important. I got to be careful with this integration when there's a tricky property. If I have this, what was t times x of t? This is a property. Over here, what happened? Do you remember? T times x of t, say again? Minus what? In terms of Laplace, it's, let me try to do it this way. Class? Minus d of x of s ds, right? Isn't that right? Y'all remember that? All right, so now what do you think it's going to be for Fourier? Take a look, isn't it J times dx of omega, d omega? What property is that, by the way? You got your book open.
Frequency derivative?
Number
9, and you see the property? Isn't it Tx of t goes to J dx of omega, d omega? You see that?
Yeah, this one has like T to the end, so that also.
Yeah, but this is gonna do,
Yeah.
problem is they do this, right? Right, and you can do that if you want, but the first, let's just leave it the first derivative, and this is actually the derivative, the nth derivative, that just let n equal 1. Follow me? We don't have to worry about more and more derivatives at this point. Now, that's a big property, it's important when we use that, right? Now, do they have the cosine or sine or e to the j omega naught t multiplying x of t in your property list? Because I'm going to show you this one, this is important. Which one do they have?
Number 10, cosine.
They have sine and cosine?
Cosine.
Just cosine? Is it cosine omega t or cosine omega t plus a phase angle?
Is omega t.
Just cosine omega t? This is real important. I like to do sine and cosine. And I'm going to put this one down here. I'm not going to use x of s. I'm just going to talk about Fourier. This is real important property. My opinion, this is called modulation. So put this down here. This is modulation. I don't know why he doesn't spend a little more time on this, but I'm sure he has his reasons. So if I have x of t times cosine of omega naught t, that's multiplying x of t by a high frequency signal. Or in my opinion, this is the way we usually think of it, this is a very high frequency signal. Much, much higher frequency than the x of t, the highest frequency interest for x of t. And this would give you AM modulation. You might even put this, call it AM, it's amplitude modulation. Now, when you take a look at this, we did the proof with Laplace. Do you remember that? I literally did the proof. I broke this cosine up into what? E to the j omega naught t plus e to the minus j omega naught t over 2, and I multiplied that by simply the x of t, right? And then I went through and I consolidated things, but ultimately it comes down to this when you do it. You're going to get 1/2, write this down, x of omega plus omega naught plus x of omega minus omega naught. I want to make one comment on this to make sure you understand. This is the transform, the Fourier transform of this. Does your book have this, by the way? All right, now this is so important. And here's why. It's saying if I have a waveform, x of t, and it gives me a frequency domain spectrum, x of omega. I want to just bring this out. So I've got x of t like this, and the spectrum of x of t in the frequency domain looks like this. I'm just going to do it this way. Call this plus omega b minus omega b, and this is x of omega. And that's some value a. And that's a triangle function. Now when I multiply it by cosine, what I get is this. When I take x of t times cosine of omega naught t, assuming omega naught here is much, much greater than omega b, the highest frequency of interest down here, then I get this. This is a over 2, and this is omega naught minus omega b. This would be omega naught plus omega b. And you're going to get something down here that's equivalent. This would be a over 2 minus omega naught minus omega b minus omega naught plus omega b. And you can see it takes that exact shape for spectrum, reduces it by a factor of 2, and shifts it out at 2 frequencies. Now you really only concern yourself with this one. But it's saying that now the entire frequency has been shifted, or the entire x of t spectrum has been shifted up to a very high frequency. And that's something you can transmit on an antenna. And you can let it go. And not only that, another antenna miles and miles away that it strikes, even though I have a reduced amplitude, you can amplify that signal. And then if you take this spectrum, which is in the frequency domain, that's now coming in, I can multiply that again by a cosine waveform, and I can recover the original. That's amplitude demodulation that we'll talk about more later. But I'm just telling you why that is so important. It's the basis for AM communications. That was the first really long-range wireless communication that was effective. There was something called, you know what the telegraph is? Just on or off, da, 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 da. Right? Well, there was a way to actually transmit that wirelessly. Marconi had it, where before AM was developed, they just had basically arc discharges. Whenever you tap it down, they would have an arc, and that would launch a wave that was really wide spectrum, but at the ship they could recover that, and they could actually, with a little amplification, they could hear at some range what you were saying, but it was all in Morse. But the first, I call it modern because you could understand the voice, the modern form of long-range telecommunications done electronically was done with AM modulation. That's why it's so important. All right? Now, there's also the sign I'm going to put down too. When I have x of t here times sine, they don't have that in your book, right? Is that right?
Right.
Let me put it a little lower. It's basically the same as this one. But here what happens, now it's going to be, not in your book, it would be j over 2, and then it's x of omega plus omega naught minus x of omega minus omega naught. Got one comment about this. The magnitude spectrum is exactly the same magnitude. The difference is the phase. You notice that j throws a 90-degree phase shift into this portion, and a minus 90-degree phase shift into that portion, which means it's odd symmetry. This is even symmetry, and it's something that later on you'll see why that's important. It has to do with the demodulation of waveforms, and it's really something that has to do with something called the quadrature processing. It's the in-phase and quadrature terms. It's much later in your education, but you have to be aware that that phase does have, it does bear, and it has an important function in signal processing, especially with radar, with my work. All right, now that's sine. We'll do one more. What's one? Both of these things come out of, and we actually had it in our properties. Remember when I had e to the minus at u of t times x of t? Do y'all remember that? Well, here, if you had x of t times e to the j omega naught t. Now, I want to say something about this. That's time domain, right? E to the j omega naught t is not a realizable time domain function by itself. If you add e to the minus j omega naught t to e to the j omega naught t before you multiply, then you have a cosine. If you take e to the j omega naught t minus e to the minus j omega naught t over 2j, you have a sine. But e to the j omega naught t by itself is not realizable in the true sense. You can't have a j, the square root of minus 1 in the time domain. I'm just trying to tell you that that is disallowable. It's interpreted in different ways to make it allowable. But for the sake of completion here, in the abstract domain, this, well, what do you think it'll render? I'll put it up and you'll see. This is the fundamental definition of x of omega. Integral from minus infinity to infinity of x of t e to the what? Minus j omega t dt, right? Now take a look at that for this waveform. Now I have x of t, right? And can't I group, how about I do this? I'm going to make this minus for a reason. We could make it plus, but I'm leaving it minus for a reason that you'll see in a second. Let me come over here and you'll see why it's so important. Now I'm going to get to the property, the save all property. Now I'm going to put the e to the minus j omega naught t times e to the minus j omega t, and I get e to the minus j omega plus omega naught t dt, right? what does that go to? Just take a look at that quick for a second. Doesn't this now appear to be as this? Where does that always appear? The argument of the transfer function, of the actual definition of the Fourier transform, right? So that means this simply becomes x of omega plus omega naught, where, and here, I'm going to tell you, where x of t and x of omega are defined this way. So if I know x of t gives me x of omega, then x of t times e to the minus j omega naught t will give me x of omega plus omega naught. Follow me on that, class? Are you with me? That's all it is. And by the way, you can create a sine and a cosine based on that relationship I just gave you, and you can prove those two above it. But that's general. That's to help you. Now, some of the other properties in there, I'm not going to go through them all. You're going to see integration of x of t, or xt, what is it, tau, d tau from minus infinity to t. They'll have the integration property, it's 1 over j omega. Take a look in your book. Do you see that without me going through it? It's very similar to what? The actual property of x, when you integrate, if you had an integration of time, or x of t with respect to t, it always brought over 1 over s, right? Times x of s, correct, class? But there's one thing that happens at 0. Do you notice it's a delta function at 0? They have delta of 0 times some stuff. Do you see that? Or delta of w, w goes to 0 is when it turns on, pardon. Delta of w times pi, right? That you see it? I'll talk about why that occurs later. I'll get to that, but I just want to tell you integral properties there. And there's a host of other properties that they have, all that parallel the Laplace properties. Take a look at those in your book. If you have your book open, you're going to see a list of Fourier transform properties that pretty much parallel Laplace transform properties, with one exception. S becomes j omega, and instead of minus s, you'll have, or minus s, you'll have just j omega. Follow me on that, class? That's the one difference, and you'll see it with the properties. But here's one thing that's much different. And this is called duality. This is the last thing I want to mention. But for me to talk about duality, now I have to take a look at the inverse Fourier transform. General Fourier transform is x of omega is equal to the integral from minus infinity to infinity of x of t e to the minus j omega naught, or omega dt. That's the Fourier transform. This is called, by the way, analysis. We're analyzing a signal. If you look at videos from the guy at MIT, Oppenheim, I think he's really good. I encourage you to go to the website and just look up MIT Signals and Systems. Make sure you get Oppenheim. It's a guy from the 80s and 90s, I think his lectures have done. Tremendous lecture, very much to the point, but he emphasizes this is analyzing a signal. The next part is synthesis. Now, if we have x of omega, say we want to filter properly. We want to create a filter. Then we want to see what the impulse response to that filter is. That's in the time domain. If we have an h of omega, transfer function, the h of t would be the impulse response, right? So for x of t, it would be 1 over 2 pi. Now this is synthesis. It's the integral from minus infinity to infinity of x of omega times e to the j omega t d omega. This synthesizes the time domain waveform. And if x of omega is the transfer function h of omega that you want, then you basically have the impulse response here. That's very important. Okay? Now, with this, I'm going to show you something about duality. You'll look at those two definitions. You'll notice the limits of the integration are the same. Right? You'll also notice the basic form is the same. Difference is there's a t there, there's an omega there. They're dummy variables, right? Both get integrated out. Omega gets integrated out there, t gets integrated out there. It has an e to the minus j omega naught t here. This is plus j omega naught t. So now I'm going to show you something. Pay attention to this. This one takes some time to think about. It's at the end of class, I want you to think about it. I got 3 minutes, I think. Now, if I take this one, Don't write, listen. I want to make it look like that. So now what I'm going to do is two things. I'm going to allow t to become omega, and then I'm going to let omega become minus t. All right? In other words, in this definition, wherever there's a t, I'm going to put omega. Remember, those are dummy variables. Understand? We interpret that as time, but it doesn't matter how. In the true sense, it's an abstract concept. And wherever there's an omega, I'm going to put minus t. Got me? It's completely allowable. First with t omega. So now, this becomes my new omega. I should use a different color. Let me use red. So this becomes omega. Red, huh? Blue. All right? That's the only place t occurred, is it not? Now wherever omega is, now I'm going to put in minus t. Got me? So this becomes yes. And that one should be omega here, by the way. Are you with me, class? All right?
Shouldn't you get an extra minus sign out of it
Yeah,
from,
that's
from going from e omega to et?
The omega would go to negative dt.
Or does
Yeah,
that not affect the magnitude of the integration?
Actually, and if you do, and here's what I'm going to say about this. Now, without getting into the hairiness of this thing, this function right here, if it's in the time domain, has to be strictly real. I'm just going to say this. X of minus t is the same thing as x of minus t. If I flip these limits, I'll get x of t in here. I'm not going to spend a lot of time on this. You're going to have to take my word on this because I don't have enough time. But if I flip those and do this, I can get rid of this. And then I can say something, and this is called duality, and I want you to listen to me. I'm trying to get to a point where I spend a lot of time on this. Duality says this. This you write down. You can look this up. This is very important. Duality says this, that if in fact you know a relationship, x of t gives me some x of omega. Now remember, this is a functional form. It's like e to the minus 5t u of t. And we know it gives me some x of omega. Then I can take the form here, x of omega, and I can replace omega right this way, and I can put t in for it. So then I can say capital X of t would render to me 2 pi times small x of minus omega. Now, what I'm saying is this. These are functional forms. E to the 8 minus at u of t will go to 1 over j omega, or 1 over a plus j omega. Agree? Now, if you took 1 over j omega and you replaced the omega with t, I would have 1 over a plus j omega here. Do you agree with me? And, I'm sorry, 1 over a plus jt, pardon me, it becomes t now here. I took omega and I replaced it by t. Then I could get the frequency domain transform of that by taking this function and wherever t was, put a minus omega in there, but multiplying it by 2 pi. This is the concept of duality. I'm going to give you an example so you understand it. Understand? With me, class? So let me go over here and give you the example before you get out of here. And I'm probably about a minute over, but this is so important. Suppose I have this. I have x of t and x of omega. Now listen to me. I'm going to start with the most basic one. X of t is delta t. What is x of omega? 1, right? Now listen. Now I have this relationship. even though x of omega has no omega in it. That is x of omega, agree? Now, if I want to, I can say, what if I have a 1 over here in the time domain? Following x of, now I have x of omega is 1, right? Now I take that over here, and I say, if I have 1 here, and I want to know what the frequency domain transfer function of that would be, what the Laplace transform of 1 would be, I could take 2 pi, and then I would take this function, that's my x of t, right? And I replace t with minus omega. And now I can see 1 goes to 2 pi delta of minus omega. How many believe that delta of minus omega is the same thing as delta of omega? Why is that the same thing in rational terms? When does the delta function become non-zero? At omega equals 0. Is minus 0 the same thing as 0?
Yeah.
Absolutely. So in this particular case, in a lot of cases, you're going to see any even function, you can get rid of this. So that can be a plus omega. Now, what does it really say? It says if you have 1, isn't 1 just DC? 1 is something where you have 5 volts since the beginning of time until the end of time. Well, what do you think in the spectrum you're going to have? Is there any change at all? Any variation of that? None. All the information, all the signal spectrum is at 1 and only 1 frequency, and that is 0. How much of it? A delta function of it. 2 pi times that. And that's something where duality directly gets you the answer. If you try to integrate this times e to the minus j omega t dt, you get an absurd answer that has no meaning. All right, but this is the power of duality. I'll spend more on that next time. I'll give you homework. The Fourier transform. All right. And about Friday. Well, you have homework to turn in. And I'm going to give you a simple quiz on Fourier transforms, but it's going to be basic. I don't want to mess with the Fourier series analysis. Basic, based on the homework entirely that I'm giving you tonight. Got it, guys? All right. Did you understand this thing? If you don't understand duality, spend some time with this. Extremely powerful.
Test will be next Friday?
No, we're discussing the test date on Friday.
Okay.
Isn't that right? So be here. How about, I hold all you responsible to get that out.